Okay, welcome to the last session of today on authentication and sequentiality. The first talk in this session is entitled Hide and Seek and the Non-Resignability of the Buff Transform by Yale Dorn, Serge Fair, Husuan Huang, Zhongwang Liao, and Patrick Schruck. And Husuan Huang is giving the talk.
Thanks for the introduction. My name is Yao Xuan. I'm a final year PhD student at CWI. This is a joint work with Yale Dorn, Serge Fair, Junjie Liao, and Patrick Schruck. The context of this talk is about the NIST post-quantum competition. Since the winner of round 3 has been selected, there has been an additional round for post-quantum signature scheme. And up until now, it has proceeded for like 2 stages. In this extra round, NIST explicitly recommends candidates to have several additional security properties. And the one we are mainly concerned with today is the so-called non-resignability, or NR for short, which says that an attacker cannot adapt a signature to verify under a different public key but the same message without knowing the message. Putting this a bit more formally, an attacker of such a NR security is given signature of an unknown message, but not the message itself, together with some public information. And then it is asked to produce another signature that's going to verify under a different public key PK prime of its choice, but for the same message. Insightfully here, we are sort of relying on the message being uncertain, because otherwise the attacker might just sign in the message using its own secret key. And here the uncertainty of the message is formally captured via either statistical or computational entropy of the message conditioned on some other information that's being passed to the attacker. In order to achieve these kind of additional security properties, oh, by the way, so this may look a bit not well motivated, but it's actually like motivated by as an extra layer of protection in case a signature scheme is misused within a higher level protocol. And indeed, there has been application that's been broken because they uses signature scheme without those security properties. Yeah, so in order to achieve these security properties, and NR in particular, Clamers et al. Proposed so-called buff transformation. What they do is they give the first formal definition of these security properties, and NR in particular, and they show that there's this generic compiler that's going to transform any signature scheme into another one, which they claim to achieve their particular definition of NR. As you can see, this is a very cheap transformation. One simply do a prehash of the message together with the public key, sign the prehash, and append it as an additional part of the signature. Also, it is explicitly referred to by NIST and relevant for various candidates on the table. However, there's a plot twist, namely recently, it has been shown that the particular definition by Clamers et al., the NR definition, cannot be achieved. And in particular, buff transformation doesn't achieve this particular notion of NR. And this basically means the security justification of buff is being flawed. And since then, there has been several alternative definitions of NR being proposed, but none of them were known to be achieved by buff. So it's sort of a natural open question to ask, does buff achieve any meaningful notion of NR? In this work, we're going to tell you the answer is a big yes. What we've done is that we introduce a so-called SNR, an alternative definition of NR in the random oracle model. And we show that buff transformation achieve this particular notion, SNR, in the random oracle model. Our proof applies to both statistical and computational entropy requirement and to both quantum and classical attacks. It's also insightful to notice, to remark that our particular notion SNR is somewhat the strongest notion on the table if compared to any other definitions, up to some minor incomparability under the computational entropy requirement. Moving on to the next, let's look at our notion of SNR. Here, this S represents the secret key non-resignability. And it's formally captured by a two-stage security game where, crucially, the attackers are now given secret key of the signature. And the first stage attacker is now in charge of sampling the message, so long as the similar entropy requirement is being satisfied. And then the second stage attacker is now given the signature of that message together with some side information, as well as the secret key. And then it is asked to re-sign the message, as we previously mentioned, in order to win the game. It might seem giving secret key to attackers may give them too much power, but here also we are conditioned on the secret key in our entropy requirement, which sort of causes this compensation of enhancing the attackers. So next, we're going to show a simple equivalent condition of above achieving SNR. Before that, I want to remark that the attacker shouldn't be able to, in order to achieve SNR, shouldn't be able to recover the message given the signature. Otherwise, it can just sign that message using its own secret key. And the crucial observation is there's a hash of the message within the buff transformation. And so in order to achieve the SNR property, it is sort of necessary that the message is hard to compute from the hash, together with side info and secret key. Well, in fact, we can show that the hardness of computing the message is sufficient in the random oracle model. And the main technical challenge, surprisingly, turns out to be showing the hardness of computing the message. So putting this, now it's the interesting part, putting this into a more abstract setting. Now we consider this so-called hide-and-seek game. It is defined as a two-stage security game played by two attackers, the hider and the seeker. The hider is in charge of sampling an input X together with some side info of that input Z, such that the certain entropy requirement is being satisfied, namely the mean entropy of the input conditioned on side info and the random oracle is high. And then the seeker is given the hash of that input together with the side info, and then it is asked to recover the input, so basically inverting the hash. The game is won if the seeker succeeds. It might seem to you that this game is trivially hard, and in particular, maybe trivially, maybe one can show that it is hard to win trivially. But here comes the tricky part, namely the input and side info may be arbitrarily dependent on the random oracle. And it is this dependency on the random oracle that causes all the troubles, and basically no previous proven technique works against this setting. As an insightful example again, consider the following side info, which is computed as the input added up with its hash. Then even though, given the side info, it is hard to compute the input X, if the attacker is additionally given the hash of that input, then it is easy to compute the input X. So what's the catch here? It turns out in this particular case, the entropy of the input condition on side info is being low. So a legit security proof should somehow be able to exploit this entropy requirement in order to show, capture all these strange random oracle dependency. So it's sort of like a blender where you can blend a fruit into a juice, but not vice versa. Finally, let's look at how this is being analyzed. So it's actually, the idea is quite simple. we simply reduce the seeker, as in the hide-and-seek game, to another guesser that tries to guess the input from only the side info, and of course also the random oracle, with similar probability as the success probability of the seeker. And then because of the entropy requirement, the guesser is not likely to succeed, so neither does the seeker. And this guesser is actually also quite simple. I mean, up to a catch, which I'm not going to mention in this talk. But the idea is the guesser is simply going to make a uniform random guess from a particular set, capital S, which is going to be dependent on the seeker, the random oracle, and the side info. And what's crucial about this set S is that so long as the seeker succeed, the input is the answer to the question is going to be contained within that set. And so intuitively, it suffices to argue that the size of the set is small. And that's precisely what we did. We argue that almost always the size of the set S is being small. We do so via some Markov bound, so controlling this via the higher moment of the size of the set. And then we control this higher moment via the so-called multi-instance function inversion game. This might seem intimidating, but what it says is just the probability of an query-bounded attacker inverting many hashes simultaneously, which, by the way, has been resolved, has been investigated in a previous work in the context of so-called time-space trade-off by Zhong, Guo, Liu, Qian in 2020, including also the quantum bound. So finally, the conclusion of this talk is that we show Buff achieve this very strong notion of SNR, basically almost the strongest definition facing all previous negative results in the random oracle model. There are still certain open questions. First of all, it is conceivable that maybe we can relax the entropy requirement into the hardness to compute the message, given side info and the secret key. And second of all, what about a more realistic modeling of the hash? Now we model hash function as a random oracle, but maybe there's for certain construction like Merkle-Damgard and sponge construction, maybe we can just have a more realistic idealization. And that concludes my talk. If you're interested, please look into the full paper, which is here at the QR code, or talk to me, and I'm happy to answer any questions.
Oh, any questions?
So there's this notion of input hiding signatures that uses perfect point obfuscation without random oracles. I wonder if this could be useful to you.
Okay. So the thing is, I guess this is something in the plain model, I guess.
Yes.
Yeah. So in this previous negative result in 2024, we show that this notion cannot be defined naturally cannot be achieved naturally in the plain model. So regardless of how the signature is being constructed. So including, I guess, also yeah.
Okay, I have one. So when you condition on the random oracle, you really mean the entire function table of
yes,
the random oracle?
Yes, the entire function table.
Okay, and then
maybe I go back.
Yeah, okay. And yet another question. So often if you have like a min entropy requirement, you can often just replace it immediately with the pseudo entropy requirement. Like,
oh, you mean the computational? Yeah. So it actually turns out a bit tricky because in the computational setting, the distinguisher in the pseudo entropy, as defined in the pseudo entropy, cannot just take in the entire function table because otherwise it's just inefficient. But then we also have a definition for that pseudo entropy, and under that definition, the result carry over to the computational setting.
So you also showed this hide and seek to be secure in the quantum random oracle model, right? In
Yes.
the QROM?
Yeah.
So in this model, I guess the green guy can make quantum queries to the random oracle, and each of those queries kind of disturbs the random oracle. So when you condition at the end, is it like you condition on the state of the random oracle after the green guy made all those quantum superposition queries? So
Yeah. So here, what we show is actually a bit stronger. We show that the hider can be unbounded, and the seeker can make constant queries or classical queries with different bounds.
oh, I see.
Yeah.
Okay.